Hi everyone. This is a video for Math 60. I am going to do examples from section 4.3 just to give you all a chance to see some more of these that you can use as you study. And I'm just going to pull these examples exactly from my version of the homework. And I'm just going to go through them one by one. So we want to reduce 18x squared over 66x to the fourth. And the way we're going to do that is we're going to find the prime factors of the top and the prime factors of the bottom. So 18 is 2 times 9, which is 2 times 3 times 3. And 66 is 6 times 11, which is 2 times 3 times 11. Good idea to do practice with prime factorizations in order to be comfortable with this process. So 18x squared I can write as 2 times 3 times 3 times x times x. I treat the variable like a prime. And 66x to the fourth is 2 times 3 times 11 times x times x times x times x. And now, just like reducing a fraction that has only numbers, I look for primes that are shared in the top and the bottom. There's a prime that's shared, so I cancel that out. And there's a prime that's shared, so I cancel that out. And also, the x's I treat as primes, so I cancel 1, 2 of the x's. And that leaves me with 3 on the top and 11x squared on the bottom. 3 over 11x squared, and that is reduced. All right, next example. Let's reduce the fraction 121x to the fourth over 66x squared. And I'm going to do this the exact same way. I'm going to find the prime factorization of the top. 121 is 11 squared, so it's 11 times 11. And remember that if you're not sure how to factor 121, just try dividing it by a bunch of different prime numbers and see if any of them work. If you were to try, none of these would divide 121, but this one does work. So 121 is divided by 11, it's 11 times 11. And then I have 4 x's because it's x to the fourth. And then I already did my factors on the bottom, 2 times 3 times 11. I did them in the previous question. And then I have 2 x's. And now I look for shared primes. There's an 11 and there's an 11, so I'm going to cancel those. And there's an x and an x, and another x, and I cancel those. And I'm left with 11x squared on the top and 2 times 3 on the bottom. So 121 x to the fourth over 66 x squared equals 11 x squared divided by 2 times 3, which is 6. And I'm done. That's reduced. All right, next question. We're going to simplify another fraction. We're going to simplify or reduce the fraction 72 v to the fourth n cubed divided by 60 v times n squared. So I'm going to do the same thing. I'm going to factor 72. 72 is 8 times 9, which is 2 times 2 times 2 times 3 times 3. And 60, well, let's do the top. And then I have 4 v's and 3 n's. And 60 is 6 times 10, which is 2 times 2 times 3 times 5. 6 times 10 or 4 times 15. I rearranged my primes to get the smaller ones first. And then there's a single v and 2 n's. And then we cancel shared primes, cancel those, cancel those, cancel those, and shared variables. One of the v's cancel and 2 of the n's cancel. So I'm left with, I'll use a little arrow this time. A 2, a 3, v, n on the top, and on the bottom, looks like I'm left with just a 5. So 2 times 3 is 6. 3 of the v's multiplied is v cubed, and an n, all divided by 5 on the bottom. And this is reduced. All right. Moving on. New question. We're going to do a two-step process. First, multiply, and then reduce the fraction 49 over 66x times 30x squared over 21. Now this is, your question says simplify the product, so it's telling you to multiply and then reduce. But actually, I'm going to recommend you do it the following way instead. First, find the primes, then cancel shared primes, and remember that variables are like primes. Then multiply. So we're actually going to do the fraction multiplication last. So 49 over 66x times 30x squared over 21. 49 is 7 times 7. 66 is 2 times 3 times 11, and there's also an x. 30 is 2 times 3 times 5, and there are 2 x's. And 21 is 3 times 7. So first I'm going to find the primes. And then I want you to remember that when you multiply fractions, you just multiply the tops and you multiply the bottoms. So let's just do the multiplication across the top. Get them all multiplied together. And do the multiplication across the bottom. 2 times 3 times 11 times x times 3 times 7. All right, so what I've done is I've found the primes and I've put them into just a single multiplication in the top and the multiplication in the bottom. And now I'm going to cancel shared primes. Here I'm not going to try to connect the loop, but what I will do is I'll circle these two 7s and then cross them both off. And I'll circle these 2s and I'll cross them both off. And I'll circle these 3s and I'll cross them both off. And also I've got an x in the top and an x in the bottom. So I'll cancel those off. What we've done is we've turned a multiplication into something that we did before. The previous three questions, this is what we focused on, canceling shared primes. So I turn this multiplication into a canceling of shared primes. And then I find the leftovers. There's a 7, a 5, and an x in the top, and an 11 and a 3 in the bottom. And now I do the multiplication. 7 times 5 is 35 times the x divided by 11 times 3, which is 33. And I'm done, and this is already reduced. There's no more reducing that I have to do because I already canceled all of the shared primes. You could multiply 49 by 30x squared and 66x by 21. And you'd find the fraction, and that would be the right answer. But then you have to do a lot of reducing. And the bigger the number is, the harder it is to split it into primes. So I like to find the primes before I do the multiplication so that I can cancel out those shared primes and not have to involve them in the multiplication. And then I also don't have to reduce. All right, next example. Okay, we're going to again multiply and reduce the fraction negative 60 divided by 36p times 84p cubed, all divided by 12. And so the first thing I'm going to do is get all of the primes. I'm going to factor these into their primes. Can't forget the negative. 60 is 2 times 3 times 2 times 5. I didn't write it in the order I normally do, but that's still the right multiplication. 2 times 3 is 6. 5 times 2 is 10. 6 times 10 is 60. 36 is 2 times 3 times 2 times 3. And there's also a p. And I multiply that. 84 is 7 times 12. So that's 2 times 2 times 3 times 7. And then there are 3 p's. And then the bottom is 2 times 2 times 3 because it's 12. Now, you could say 84 is 7 times 12 and just cancel the 12s right away. That's fine. But I want to show you the prime method because this is the way that always works. I can write it just as a long chain. Don't forget the negative. 2 times 3 times 2 times 5 times 2 times 2 times 3 times 7 times p times p times p. And then I'm going to divide all of that by 2 times 3 times 2 times 3 times p times 2 times 2 times 3. There are a lot of numbers floating around, but if you're methodical, you can do your cancellations. There's a 2 and a 2, I'm going to cancel those. There's a 3 and a 3, I'm going to cancel those. There's another 2 and a 2, I'm going to cancel those. And then I have, well, I've got a 2 and a 2, cancel, a 2 and a 2, cancel, and a 3 and a 3, cancel. And then I have a P in the top and a P in the bottom, and I cancel those. And I'm left with 5 times 7 times P in the top, and a 3 in the bottom. Don't forget your negative. 5 times 7 is 35. P squared all over 3. That's the answer. That's fully reduced. Now I do want to do this question again because getting all the primes always works. But as you saw, there were a lot of primes floating around, and maybe we can make our job a little simpler if we look for factors that are a little bigger than just the primes. So for example, I know 60 is 6 times 10, and I know 36 is 6 times 6. So now the 6's cancel, and I made my job a little easier. And I know 84 is 12 times 7, and there's the p cubed. And there's a 12 right there, and so that cancels. And so what I end up with is negative 10 times 7 times p cubed all over 6 times p. P cubed is p times p times p. And so one of those cancel. And I get negative 10 times 7, so negative 70p squared over 6. And I recognize that 70 and 6 are both even. So that's 2 times 35p squared over 2 times 3. And I get the same answer. There's the negative. Don't forget the negative. I get the same answer as the other way. I didn't split it completely down to the primes because I decided I didn't need to. So this is something that you can work toward, but when in doubt, getting it all the way down to the primes will always work. Okay, next question. All right, another one, very similar. Negative 63 over 9w to the fourth times negative 45 w squared over 27. And we're going to multiply and reduce, or we're going to do the multiplication and reducing in the other order. So let me start with 63, which is 9 times 7. I'm not going to go all the way down to the primes because I have a 9 in the bottom already. And similarly, negative 45 is going to be negative 9 times 5. And 27 is 9 times 3. All right, so this is an example where I decided not to go all the way down to the primes, but to look for common factors in the top and the bottom. So negative, or the 9's cancel. I still have the negative. I'm going to have negative 7 over 4w's. And I'm going to have a negative 5, because that negative's still there, times 2w's. It's a multiplication. And a 3 in the bottom. And I look for shared primes. I don't have any shared primes, but I do have 2 shared variables. The 2 of the w's on the top cancel with the w's on the bottom. Negative 7 times negative 5 is positive 35. No more variables on the top. And then I have 3 times ww, which is 3w squared. And that's my answer. This one is fully reduced because 3 doesn't go into 35 because they don't share any primes. All right, moving on. Next question. We're going to start adding fractions and then simplify. Add, then combine. By simplify, we're going to be combining like terms of 10n minus 11 divided by 2x plus negative 17n plus 16 all over 2x. Whenever you add fractions, you ask, do they have the same denominator? And since they do, I can just add the numerators over a shared denominator. So I'm going to have 10n minus 11 plus the quantity negative 17n plus 16. I strongly recommend that your first step includes parentheses around the second term. And let's see if there's going to be an example y. I will do an example y to show you why that's important. All right. There I've got the top, there I've got the bottom. Now I'm going to combine like terms. 10n minus 11 plus negative 17n is negative 17 or minus 17. And then plus the positive 16 gives me plus 16. Divide all that by 2x. I combine like terms. I have a 10n and a negative 17n. And I've got a negative 11 and a positive 16. So 10n minus 17n is negative 7n. And negative 11 plus 16 is plus 5. Divide it all by 2x, and I'm done. There's a 2 in the bottom, but there are no shared 2's in the top, and the n and the x are different variables. All right, now let's do another fraction. The fraction here will be simpler, but I want to show you why it's important to have your parentheses. Let's do x plus 1 over 3 minus 2x plus 5 also over 3. So these have the same denominator. But what's hiding in this fraction, if you think way back to my PEMDAS, what's hiding in this fraction is when you have a division sign, there's a parentheses around the top. It's actually around both of them. The one at the front's not so important for this example. But the one at the back is super important. If I don't have the parentheses, it looks like I'm adding a 5. But because there's an implied parentheses, I need to include that parentheses when I do the division or when I combine the terms. Because I'm subtracting 2x plus 5, which means I'm subtracting 2x, and I'm also subtracting 5. So this becomes x plus 1 minus 2x. And the negative distributes to both of the terms, so it's also minus 5. Without that parentheses, I would be adding the 5, which is wrong. So when you build your single fraction, put a parentheses at least around your second term. And now I combine like terms. I have an x and a minus 2x, which is a minus x. I have a 1 minus 5, which is negative 4. And I'm done. Okay, next example. We're going to add and combine like terms for 3 over 2c plus 9 over 8. So these have different denominators. So my first step has to be to get them over the same denominator. So I ask myself, what is missing from each denominator? Two c is missing a 4 because that will get me to the 8. 2 times 4 gets me to the 8. And the 9/8, that's missing a c because there needs to be a c in the denominator. Remember, you treat c just like any other prime. If it's missing from one of the pieces, then you multiply by c over c. And I get 3 times 4, which is 12 over 8c, plus 9 times c, which is 9c over 8c. And now they do have the same denominator, so I can add the numerators over the shared denominator. And there are no like terms in the numerator, so I'm done. I've added them, but there are no like terms to combine. 12 is a number, 9c is connected to the variable. I cannot cancel these c's because it doesn't show up in the other term as well. So I'm just completely done. All right, next example. Let's see, we're going to combine 3 over 4v minus 7v over 12. We're going to do the subtraction and then combine like terms. So again, I ask what's missing. Well, to get from 4v to a 12, I need 3, because 4 times 3 is 12. And to get from 12 to 12v, I just need a v. 4v times 3 is 12v, and 12 times v is 12v. So multiply the numerators to get 9, and the denominator is 12v, and then I have 7v times v, which is 7v squared, also over 12v. And so now I can do the subtraction of the tops over the shared denominator, and I'm done. Because the tops, they are not like terms, so I can't combine them. And I don't have a v in both of the tops, so I can't do any cancellation. All right, let's keep going. Oh, we don't need to keep going. Those are all the questions from 4.3. So what I've done is I've done an example of every question on your homework, plus one extra example. And so you can watch these and follow along, and then use those to help you as you do your homework. Thank you for watching.